the same. So the edges are already completely recoded. No 0 to 1 on the back. Like, bro, it's like this. Really bad. No, I don't. Like, I've never probably it's like. So kind of like if you drop the water. Okay. We have not had a new Abrahamic religion for over 1,400 years. It's giving a lot of for more crusades. Yeah, okay. What should the four places? You need to study. All our they say you can like but like they know it was common that like what it was called. It wouldn't be an Abraham, but what would Abraham is eating from this. Yeah, but it's God came. You got a 4, right? You get one that's not right. Oh yeah. No, they're literally teaching the Yahweh. That's no, like you raise against him like wrong. No. Have you ever read it? Straight up.
Okay, so today we're talking about absolute extrema extreme value theorem. So this yeah, this will be basically our we're basically at the halfway point of AB curriculum. So after, there's a lot here, but after this, we're going to basically be moving into second semester content for AP Calculus. So we're almost done with all of AB content. So our calendar after the quiz on Monday, we'll do the rest of the theorems that we haven't seen yet are going to come up here. So extreme value theorem, Rolle's theorem, mean value theorem, those are the big ones. And we're going to be having to look at a derivative graph and being able to interpret it. So that's a big part of the AP exam, and we want to be really comfortable with that. Optimization is kind of a word problem, kind of word problem-ish, kind of like related rates. It's in the curriculum, so we go over it, but it doesn't show up on the AP exam that often. But it's not a big deal. I mean, it's just finding the derivative, setting the derivative equal to 0, and finding critical points. But it's just in the word problem format, so it feels a little bit different. But really, it's just finding critical points. And then, so that first week of October, we're going to have a unit test, and then we start second semester content here with antiderivatives. Yeah, and we'll be able to complete all of AP content by the time we reach end of the semester in December. All right, so some definition here. Extrema is plural for max and mins, so maximums and minimums, so basically peaks and valleys of graphs. So if we have any hill of a graph or any valley of a graph, we call those points a relative maximum or a relative minimum. The reason why we call it relative is because any maximum that you find immediately to the left and to the right, it's higher than the points to the left and to the right. So relative to that region, it is the maximum value. And here, this point within the immediate regions next to it, it is the lowest point. So it's relative minimum. And here, this is also a relative maximum because in relation to the points immediately to the left and to the right, it's higher than those. We also, sometimes you may also see local as well. So local, relative, usually we use relative, but sometimes you may see local. It just means the same thing. Now this point is a relative max because it's a hill of a graph, but we also can consider this an absolute maximum because over the entirety of the graph, it is the highest point. So it falls into two categories. It's a relative maximum because it's a hill of a graph. It's also absolute max because there's no other point throughout the graph that's higher than that point. There is a relative minimum, but this graph does not have an absolute minimum because negative infinity doesn't count as an absolute minimum. It is not a physical point that we can locate. So for this graph, there is an absolute maximum, but there is no absolute minimum. So we never want to call infinity or negative infinity as absolute max or absolute min. It needs to be a physical point that we can locate to call it an absolute max or absolute min. Okay, so on the closed interval, if we have endpoints that are defined, this graph would have a relative minimum because there is a valley for our graph. This also is an absolute absolute minimum as well. There's no other point lower than this point. This is an absolute maximum, but it is not a relative maximum. The reason why is because I have to be able to compare a point to the left and to the right of it in order to call it a relative max or relative min. So here, there's no other point to the right to compare it with. So it is the highest point, but it is not a relative maximum if it's an endpoint. So endpoints, we can never call endpoints a relative maximum or relative minimum. Okay, now if this is an open interval, meaning that the points are not defined, but we can get infinitely close towards that point, there is still a valley of the graph. This would still be a local minimum, a relative minimum and an absolute minimum. But there would be no absolute maximum here because if I find a decimal really close to that hole, I can always find another decimal even closer. So we can never pinpoint an absolute maximum highest point on this graph. Okay, so extreme value theorem, which I'm going to abbreviate as EVT. It says that if a function is continuous on a closed interval, so remember how with IVT, I would take off a point if you didn't indicate the condition that the function is continuous. So this is going to apply as well. So if I ask you, so basically for any theorems that we're going to be applying and using, there's always a continuity portion to it. So there are theorems that have more than that, but at the very least, there's always that continuity portion. So we want to make sure that we include that continuity condition as part of applying a theorem. So we'll get practice with that, but just kind of give you a heads up. Just like with IVT, I'm going to expect you to be able to state that the conditions for theorem. So if a function is continuous on a closed interval, meaning there are no breaks in the graph, then it has both an absolute minimum and an absolute maximum on the interval. The only break from the only exception to this rule is unless it's a constant. meaning that if it's just a horizontal line, if this horizontal line, then there is no max or there is no min. But in any other situation, if the graph is continuous, we can always locate an absolute max and absolute min if it's on the closed interval. Okay? If there's an ending point and starting point for the graph. This is a continuation of that theorem. If a function is continuous on a closed interval, then the absolute maximum will either be at a critical point or at an endpoint. I'm going to highlight those ideas at the bottom of the page. So critical numbers are values in the domain where the derivative of a function is either 0 or undefined. So 0 slope could look like this, but undefined could also look like this as well. Okay, so we want to consider places where slope is 0, but we also want to consider places where slope is undefined, because slope undefined could also end up being an absolute max or absolute min on the graph. Relative extrema only occurs at critical numbers, but not all critical numbers are where relative extrema occurs. Okay. So for instance, if I have a slope 0, this would be a critical value because the slope 0 will show up when you set the derivative equal to 0, but not every critical point is a relative max or a relative min. Maximum and minimum values refer only to the y values at that point. So on the AP exam, if it says, what is a maximum value? It's kind of vague, right? But we have to understand that if AP exam, if College Board, if they mention the word value, we have to understand that it's not talking about the order pair. It's not talking about the x value. It's just talking about the y value. Okay. It's like asking, what is the maximum height, right? If there's a maximum height, you wouldn't provide the time. You would provide the value, the y value at that point. So the reason why that if we're trying to find an absolute max or absolute min, the only points we have to consider are endpoints and critical points, because those are the only candidates where absolute max or absolute min can occur. If a function is continuous, I'm going to have to consider my endpoints, because we can draw the graph in a way where the endpoints end up being the highest or lowest points. We can also see an instance where the valley or the peak of the graph ends up being lower or higher than any other point. Right? So we don't want to consider any other candidates besides endpoints and critical points. So we always have to, so if we're trying to find an absolute max or absolute min on a graph, and we're doing this without the use of looking at a graph, we can limit ourselves to just looking at the endpoints, testing the endpoints, plugging the endpoints into the original function, and then also finding the critical points and plugging those into the function, and just compare the y values. The highest y value would have to be the absolute max on the closed interval, and the lowest y value would have to be the absolute minimum on that closed interval. Right. So to find critical points, we're going to be setting f prime equal to 0. And if I want to find a place where the slope is undefined, I would need to set the denominator of the derivative equal to 0. Now, not all derivatives will have denominators. So if a derivative does not have a denominator, then we don't have to worry about any slope undefined. We don't have to worry about any sharp turns. We just have to worry about potentially looking for slope zeros. And then at the same time, not every graph on the closed interval will have critical points. So if there are no critical points, then we just have to test the endpoints. So sometimes you may have nothing but 2 endpoints to test, and that's fine. Right. But if it's a closed interval, you're going to have at least 2 candidates. Okay, all right, let's go to page 2. Right, so these are the extreme value theorem steps. The first is confirm function is continuous on the closed interval. So just like how we did with IVT, we have to look at the function, look to see if there's a denominator. If there's a denominator, is there a vertical asymptote? And then if there's a vertical asymptote, does the asymptote impact or interfere with my interval? If it doesn't interfere with the interval, then we're safe. Our function is continuous on a closed interval, and we make that statement. And then if we can confirm the function is continuous on a closed interval, then we go ahead and try looking for critical points. We find a derivative, and we set the numerator and the denominator of the derivative equal to 0, assuming that there's a denominator. Okay, if there's no denominator, then just set the numerator equal to 0. But if there is a denominator, we don't want to ignore that, because if there's a slope undefined on the graph, if there's a sharp corner, that sharp corner could end up being an absolute minimum. So we want to make sure we consider all of our candidates. After we find all of our valid candidates, then we plug them all into our original function, and then we compare the y values. Highest y value is your absolute max. Lowest y value is your absolute min. Now, what do I mean by valid candidates? If I find a critical point, in what situation will we not consider that critical point? Where does the critical point have to live in order for us to apply it, to use it? Yeah, it's got to be in the interval, right? So we got to make sure that after we find our critical points, we compare with the interval, right? If it's not part of the interval, it's not part of our problem. And so, we've had practice with that with intermediate value theorem. So we're kind of carrying those concepts into all these future theorems that we're going to see in this unit. Okay, so here's example 1. We have our function 3x to the 4th minus 4x cubed. Do we have any issues with continuity, or is this function continuous? No issues. Continuous, right? This is a polynomial. There's no asymptotes, there's no holes, but we want to spend the time to write out our condition. Okay, so our function is continuous. It's continuous everywhere, but we only care about the interval, so we want to make sure we just stress that we are confirming our function is continuous on our closed interval. So basically, anytime we apply a theorem, there's going to be multiple theorems in this unit. Always start off with your continuity statement. Okay, I'll be looking for that on the test. I'll be looking for that for you to earn full credit. Okay, we already have 2 candidates to test, right? We know we have to test f of 0. We know we're going to test f of 2. But we also want to see, are there critical points that are other candidates to consider? So to do that, we're going to find f prime and find critical points from f prime. So we go through power rule. There's no denominator, so we know there's not going to be any sharp turns. So we just set f prime equal to 0 and factor and solve. I'm going to get 2 critical points. What are my 2 critical points? 0 and 1. Okay. Now 1 falls between the intervals, so that is a valid candidate. We are going to test the value at 1 to see if it ends up being the highest or lowest point. 0 is a duplicate, so we were going to test 0 anyways, so we don't have to consider that, right? We're going to test 0 anyways. So we have 3 candidates, right? We have 2 endpoints and 1 critical point. So then they all get inserted into the original function. F of 0 equals 0. F of 1 is -1. f of 2 is 16. So we can tell by looking at these y values, right, that the highest number will be where the absolute max is. Lowest number will be the absolute min. So our absolute max value is 16. Our absolute minimum value is -1. Okay. In the textbook, they would refer to absolute max or absolute min as ordered pairs, but on the AP exam, they are just looking for the y values. So I want to just have us practice just doing the y values, so that so sometimes it's tricky where they ask you for absolute max and then they give you a choice of either the x or the y value, and the x value will be incorrect. So I want us to just have us practice writing it out and just referring to absolute max as the y value. So we're going to say the absolute max value is 16. So I don't want to see 2 comma 16. I want to just see one number, 16. Absolute min value is -1. And the reason that I want us to do that is I want us to connect the word value with y value. Value is y value. You wish that on the AP exam, they would just specify it. They would just say, what's the absolute max y value? But they just use the word value, and we have to just understand that they're talking about the y value. So that's really it. We're just doing variations of these problems, but that's basically the steps that, yes. No, we don't have to, yeah, that's good. That's a good question. For extreme value theorem, you don't have to write any because statements. When they say justify, they just want to see that you are stating your condition, and then you are finding the appropriate candidates, and then you're making the conclusion based off the candidates. So yes, there are theorems where you got to be wordy with because statements and all these, but with extreme value theorem, it is just the work. The work is your justification. Okay, example 2. First thing is to establish, do we have any issues with continuity? This is raised to the 2/3. So anything that is a cube root, there is no issues with negatives inside the root. So our function is continuous on the closed interval, no issues with continuity. Next up, we have 2 candidates, but we want to see if there are additional candidates that we can apply. So we're going to find f prime and look for candidates from f prime. What rule do we have to use to find the derivative? Chain rule. Outside derivative times the inside derivative. Let me get f prime cleaned up so I can see the numerator and denominator clearly. Okay, where do we look for critical points? And numerator, okay, in general, right? In this case, numerator won't produce anything, right? We set 2 equal to 0, there's nothing there. But we also, if there is a variable in the denominator, we also have to set that equal to 0, right? Because slope undefined could also be a candidate for absolute max, absolute min. Okay, so nothing from the numerator, but the denominator will give us something. Okay, so divide by 3, cube both sides. I get x minus 1 is equal to 0. I get x equals 1. I found a critical point, but is this critical point one that I want to use? No. No, why not? It's outside the domain. Yeah. So if there are no critical points, and the function is continuous, we still move on with extreme value theorem. It's just that we only have 2 candidates to test. All right, so it's not like, oh, there's no critical points, so everything breaks down. It just means that we have less values to test. Okay, so we only have to worry about f of -1 and f of 0. Make sure that you're now inserting back into the original function. Now we're looking for the physical locations on the graph and see which one is higher and which one is lower. Okay, -1, I get -2 raised to the 2/3. That's going to be cube root of 4. Plug 0 in. I get -1 to the 2/3. That's just going to be equal to 1. Cube root of 4 is slightly greater than 1. So this is where my max is. This is my minimum. But I want us to practice writing it out, just mentioning the y value. So we're going to say absolute max value is cube root of 4. Absolute minimum value is 1. So no mentions of x values, no order pair, just the y value. Okay, any questions? Mm-hmm. Yes, yeah. If the test ends up where it's a messy number crunching, then I'll definitely give you a calculator. But if it's manageable, then I'll do it without a calculator. I'll let you know whether calculator or no calculator. Yeah, I'm never going to give you a heavy number crunching quiz or test without a calculator. All right, example 3. First things first, we will have to establish continuity. So from 0 to 3, now we see that if it's a square root, there is a natural restriction, right? So here we know that anything that is where x is greater than 3 is going to cause a negative inside the square root. But anything from 0 to 3, we're safe, right? Plug 0 in, I get 3. Plug 3 in, I get 0. Root 0, square root of 0 is still a real number. So we checked all the numbers between 0 and 3. We're safe. There's no issues with continuity. So we want to make sure, though, that we state our condition. Okay. We know that we're going to test 2 endpoints, but we also need to find critical points. To find critical points, we need to find the derivative. To find the derivative, what's needed? What process needed? Product and chain. Yeah, there's a little bit of chain because that's square root. We got to worry about that outside inside portion. Okay, let's try that. See if we can do our derivative process there. I'll work on the problem as you guys try it as well. Now, in order to effectively find our critical points, we do want to compress all this down to one fraction so that we can cleanly set the numerator and denominator equal to 0 separately. So here on out, it's just algebraically trying to common denominator and clean everything up. Any questions with the derivative, though? So here's my separate fractions. They don't have the same common denominator, so my common denominator is going to be 3 parentheses 3 minus x to the 1/2. So I need to balance this first fraction with the 3 minus x to the 1/2 up top. So square root times square root, I'm just left with that expression without the radical. Now this can merge to be okay, so there's my cleaned up derivative that will allow me to clearly find my critical points from the numerator and denominator. Are we okay so far? All right, so we set the numerator equal to 0, set the denominator equal to 0. What do we get from the numerator? X equals 2, right? And the denominator, we get x equals 3. So 3, we were going to test 3 anyways. It's just a duplicate, so we can ignore that. 2, are we going to keep 2? Yes, it falls between 0 and 3. So we have 3 candidates to test. We need to find the y value at 0, find the y value at 2, find the y value of 3. Now we see a duplicate, but it doesn't really matter, right? Because we only care about the y value anyways. So our absolute max value is 8/3. Our absolute min value is 0. Okay, that's really all there is to it. I think the most difficult part is the whole derivative process, right? I think that's the messiest part. If you're having to do this is as difficult as it can get, where you got to do a combination of multiple derivatives and then having to do common denominator, and then but making sure that you find your candidates from both the numerator and denominator, and then using them to make your conclusion, as well as your endpoints. So I see some students where they just test the critical points and not the endpoints. So make sure you also consider the endpoints as well. Those are also always valid candidates, not just critical points. Okay, any questions with extreme value theorem? Yes. Wait, say it again?
As the same number of values, it can still like all the like the serum.
Oh, okay. You mean like duplicate ones?
Yeah.
Yeah, it doesn't, yeah, if it's duplicate, then just count it as just one, right? Because you're not going to be asked to find the x value. So if this is a duplicate and it does end up being the highest or lowest value, they just say that's the highest or lowest y value. You don't have to worry about the x value. Yeah, so that's why I want us to just focus on the y values, since we don't really care about the x value. Okay, there's homework for 5.1 with the extreme value theorem, but this will be due on Tuesday, since Monday you guys are taking the quiz. Okay. I want to see if I can do one problem with you from your review. We didn't get through all of number 9 in the quiz review, did we? No, okay. So let's turn to our quiz review. For number 9, did we get through all of part A? Or sorry, where did we stop for number? Did we finish A? We did, okay. All right, so we finished A, and then part B says, at what rate is the angle theta changing at that same moment? So we're going to rely on the original variables where information is given. So we have, this is the data that's provided for us at the beginning of the problem. So we know that if we're trying to find rate of change, this data, I'll have the figure drawn for you, so you don't have to guess where theta is. I know this problem, I didn't really specify where theta is. But theta is in that bottom corner there. And all we need, if we're trying to find d theta dt, is we have to create a trig equation that hits theta and two sides. So we want to use the two sides where original information is given. So in this case, we want to use tangent. Okay, so tangent of theta is equal to y over x. These are the variables. We have to go through quotient rule on the right side. So let's do our derivative. Tangent theta becomes secant squared theta, d theta dt. Remember related rates. Every variable gets impacted by time. And then we start our quotient rule on the right side. F prime g minus f prime all over g squared. Everything here we can pull from part A. We've already gathered all that data. But what's different about trig related rates is we have to find a replacement for that trig ratio. So we go to the side and we draw a triangle for that moment in time. And we have all the x and y and z values that we need from part A. So x is 20, y is 10, z is 10 root 5. And we want to step to the side and say, what is secant of theta? Secant of theta is hypotenuse over adjacent. It's the reciprocal of cosine. So 10 root 5 over 20, which reduces to be root 5 over 2. Now that we have the ratio for secant theta, we can go back to our problem and we're asking for secant squared theta. So we'll do root 5 over 2 squared. And then that's the last piece. Now we can just do a bunch of rearranging the numbers and trying to get it down to a number. Now, when you're solving for d theta dt, your units of measure is always radians per time unit. Okay, never degrees, always radians per time unit. So root 5 over 2 squared reduced to be 5/4. The right side, I just enter all that in the calculator. I get negative 550 over 400 divided by 5/4. The same thing I multiplied by 4/5. That reduced to be negative 1/10. And my units for d theta dt is always radians per time unit. In this case, radians per second. Part C says, find the rate of change of the area of the triangle. Sorry, I didn't indicate that on your copy. I meant to say area of a triangle. So we know area of a triangle is 1/2 base times width. Sorry, 1/2 base times height. In this case, x is the width, y is the height. So we have to go through product rule. F prime g plus f g prime. Pull all your values from part A. d dt is negative 15. My units of measure. Look at my derivative variables here. A is area. Area is a two-dimensional unit, so square meters. Time is seconds, so square meters over seconds. Okay, any questions here? Thanks. So bottom of the page, again, these are the topics that are going to be on the quiz. Not all of these will show up. So, but we want to be familiar with all the variations of related race problems to review. So you guys have the weekend to work through the additional problems I have in your packet. And then on Monday, I'm just going to pick out problems from the packet to work through. Any questions? Okay, I'll send out a reminder this Sunday. Monday help session will be 7:15 in the morning. If you want to join virtually, I will have a Teams link. So I will send that through Remind. You can join through Teams. And I'll also remind you Sunday night to bring your calculator. All right, come get your phones.
On the review, on this page, are we allowed to use your calculator to like find out what times the particle changes directions and like, what's the particle moving from like, can we use our calculator here?
You can, but I want to see your velocity sign line. I want to see your steps. Yeah. But you can obviously calculate to confirm. Yeah.
No, I mean, that's always.
You get your.
Typically with position, you don't, I think the only time you have to worry about negative position if you think about it, because it's always final position minus initial. It ends up being negative in this one. Velocity, if I plug a value, if I plug a time value to velocity, I get a negative number. That means at that moment in time, it's stuck.
Same, but
Like if I'm plugging a time value to the velocity, it's a positive number. Typically, yeah. Unless they specify, oh, we're moving along the y-axis, and they would have to specify, okay, positive is on this. But normally, if we're doing particle, I'm going to use particle motion words.
You know what the type it is or what? 530.
Yeah.
Acceleration, positive acceleration.
Bro, at that, I mean, the game is like.
That
goes so.
the velocity is moving towards a positive.
It's hard to play the game.
So like, if my velocity was 2 to 3 to 4, my acceleration will be positive. And if it's like from negative to 3 to 2 to 1, my acceleration will also be positive because my velocity is moving in a positive direction.
Thank you.
Anything else to provide?
Have you taken anything, Doug?